Thank you very much, Professor Wang and Professor Liu, for the very kind invitation and the kind introduction. It is really a pleasure to be here. I have tried many times to come and visit USTC, and I'm very, very happy to be able to do so this time. It is my first visit to Hefei, and I'm very, very pleased, to finally, be able to be here and see all the fantastic work that is being done here. So this presentation is about architecture, technology, competence, and fire-safe design. And you will wonder why all these words are together in the title. And they all have a reason to be there. Fire safety is a discipline that is funded in fundamental science. And when you look at the problem of fire safety, you think of issues like radiation, for example. You think of soot chemistry, the production of soot, and how that affects, for example, radiation fields. You think of pyrolysis chemistry. You think of buoyant entrainment and complex fluid mechanics. You think of structural mechanics and the interaction between structures and the heat that is being produced by the fire, and all these different aspects that fall straight into the realm of the physical and the chemical sciences, and in many cases they even intersect with biological science and psychology and social behavior when you're looking into the interaction of the fire with humans. From processes like skin burns that are complex bioengineering problems to problems like egress that require the understanding of the psychology and sociology of human behavior. So all these elements are fundamentally in the remit of science. Nevertheless, they are deeply embedded into the way in which we design our built environment. And in reality, they are many times driven not by the science, but by the creativity of individuals such as architects. Now, architects, and this is not meant to be as a criticism, but architects are not scientists. Architects are very creative people that use technology and use concepts such as space and volume to try to create an experience for people within buildings. When we look at rooms like this, you realize the concepts that architects are putting in place for you to be able to see the screen properly, for you to be able to be comfortable with the lighting, for you to be able to be impressed in a positive way by the aesthetic of the room. And that is not a space that is associated to science, but is more a space that is associated to social behavior and art, creativity. So immediately you realize that fire safety is in a crossroads, and in that crossroads between the science that underpins fire safety and the application, which is more driven by creativity, art, and social behavior. So that intersection is very complex, and it is very, very complex in that it defines itself as a function of technologies, because architects have to implement buildings and buildings require technologies. So you're going to have technologies like photovoltaics, lithium-ion batteries, lighting, materials, for the carpets, for the furniture, for the wall linings. All these things are going to be very fundamental technologies that are developed for the purpose of creating the experience that the architect wants. But nevertheless, every single one of these technologies affects the way a fire will behave. So in essence, the links between technology, science, and architecture are extremely complex when it comes to fire safety. And we need to be very careful that fire doesn't become a constraint. Now, what do I mean by a constraint? Architects have objectives. They want to give you the right experience. Those are the drivers. Environmental needs, for example, are a driver to create more sustainable infrastructure. These are the drivers. Constraints are elements that stop you from doing things, that basically pull you back. They don't walk with you in the development of the concept of the building, but they are basically stopping you from doing things that might not be safe. Now, we don't want fire to be a constraint. We want fire to also be part of the objectives and the drivers of the design process. And for that, we need to interact with architects in a way that they understand how fire can inspire them. You know, how fire can actually give them ideas of how to design better buildings that at the same time are fire safe. Not buildings that they design the way they want, and then we tell them that they cannot be built that way because they're not safe. We want to walk with them in the process. So how do we integrate all these things? Science, technology, architecture, how do we put them together? Normally, and this is the part that is the most complicated, is through regulation. Why regulation is so important? Because it is the responsibility of the government or the state to guarantee that when you are in a room like this, you are safe. And we create a set of rules that govern the interaction between science, technology, and architecture. And those set of rules many times bring us to the right place where architects and fire scientists are all working together in delivering the best possible building. But in some cases, when we don't do things correctly, those rules that we put in place can bring us to a very, very difficult place in which science, technology, and architecture enter into a conflict. So we try to really understand why and how we can deliver something that brings all these things together in a way such that actually provides the best possible built environment. So this is the subject of the talk. So this complex interaction, and we're going to be looking at science, technology, and the process of discovery and creation. Now, at the core of this is the motivation, and science is a process of discovery that doesn't have to have an objective. It is how you discover different phenomena, how you understand them, and how you represent them, many times in mathematical form. While creation is the kinds of things that architects and artists do, which is create something that is new, that is different, that is unique, that provides an exceptional experience. And all the things are all intertwined through the use of technology. So let's look at what the outputs are. So when you're talking about technology, you talk about methods, you talk about tools, you talk about products and solutions. And when you talk about creativity, you talk about architectures. So in a way, these technologies that we put in place that are fundamentally based on science are used to develop this method, these tools, these products that then architects are going to be using to create our built environment. And we need to be able to make sure that the way in which these technologies are being used, that are underpinned in science, but that at the same time enable in a creative way the architect to deliver what they need to deliver, which is the best possible built environment. So this is the world in which we exist, and it's not a simple world because we speak very different languages, and these languages are not necessarily compatible, and regulation many times is a translating tool that enables us to communicate together. Architects understand the rules that we're putting in place. They don't have to understand the science that underpins those rules. So the built environment is also constant evolution, and we have and experience new challenges every day. So I took out of Google 2 photographs of Hefei, and one that represents the way we used to do things in the past, and one that represents the way we do it today. And when you look at the two, you realize that the challenges are very different and they evolve on an everyday basis because cities are not stationary and they're not going to stay that way, as we look at it. And as we introduce new technologies, we introduce new changes, and those changes can be actually quite drastic. Now, let me give you an example of how the world has changed. So this is a story of tall buildings. Now, if we look at the way in which tall buildings have evolved, and we take as a reference the tallest building in the 1970s or 1980s, we were talking about potentially the World Trade Center or the Willis Tower, the Sears Tower in Chicago, as being the tallest building in the world. And we can see that between the 1970s and 2000, there was a very small increment. The world of tall buildings was stable. Now, all of a sudden, we started building taller. And particularly in China, we've seen a massive proliferation of tall buildings. And eventually, we decided in the 2010s to build the Burj Khalifa that still remains the tallest building in the world, which is now in the process of being surpassed by a building that is 1 kilometer tall. So you can see that there was a steep increment that almost doubled the height of the tallest building in the world in a period that was actually very short. Now, in a similar way, we have experienced a massive increase in the maximum height of timber buildings. And this has been driven by two things. One, the environmental driver that looks for sustainable construction materials. And two, by the development of new engineered timber products like cross-laminated timber, glue lamps, LVLs, all these different products that have entered the market and have transformed our capacity to create structures that are reliable when using timber. The problem with timber was an issue of reliability, and that problem has been solved with these new engineered products. The technology enters the market. Now, we have tried to adapt our regulation to reduce the barriers to height and allow more timber to be used in tall buildings. Now, as a result, the maximum building height for timber buildings has almost tripled in a decade. This is an extraordinary transformation that basically puts us in a position of great challenge, because tripling the height of the tallest timber building is a very, very significant fire safety challenge, because obviously timber is a combustible material. Now, the problem is even more complex, because in the case of non-combustible structures, the change has actually not been as significant, because while the Burj Khalifa is a much, much bigger building, all the other buildings that are in that diagram are actually not that tall. And in essence, we have more or less remained within a 50% increase. And the number of extremely tall buildings, the super tall, has actually not been as significant. Instead, when we look at what is happening with timber, the number of very tall timber buildings is very large, and they all move in the direction of the 300, 200%. So we have a very large increment in the number of tall and very complex buildings. This is the way the world changes, and we need to adapt. We need to bring the science, the technology, and the architecture together through regulation that enables them to work together and be able to cope with this dramatic change that is constantly happening in our built environment. So, safety and change, and the question is, how do we cope? So how are we going to do this to try to keep the pace of how technology is driving, how environmental drivers, how political motivations are driving the changes in our built environment? Now, this is a very well recognized process that we really need to understand very carefully, because it actually defines and enables drivers while properly account for the constraints such as fire safety. So what is the cycle that eventually brings us to the right place? So this cycle always starts with investment on research. So you invest resources in developing research, and that research is going to develop new science, new technologies, new products, new models, new activities. But those are the byproducts. The real product of that investment in research is research-led education. So in essence, you are developing competent professionals that not only understand these new technologies, these new tools, these new products, but they also understand their limitations. They understand their impact on safety. They understand how those products have to be used in the built environment correctly. Now, these competent people that stem from research-led education effectively are going to support governments in understanding how to evolve that regulation so that the regulation can continue to translate this ever-evolving language. The language keeps changing, and somebody has to keep translating it, and that translation is the regulation. So if the regulation loses pace with what is happening, then the translation becomes poor. And I'm sure you've all experienced the translation on your phones. And sometimes your translation is very good, and sometimes your translation is very poor. And when your translation is very poor, what happens is confusion. And when you get confusion, you make mistakes. So if we don't have the competent professionals that understand the tools, understand their application, and understand particularly their limitations, we will never be able to inform government so that they can evolve the regulation in a way such that it continues to translate the knowledge that is emerging from the science to the creation or the architecture. So once we have that evolution of the legislation or the regulation, then we get positive outcomes. Now, positive outcomes are welcomed by society because they bring societal benefit, and that reinforces the cycle and makes us believe that if we continue to invest in research, we will get new developments, we will get new competent people, and that new competent people will evolve the legislation so that the cycle continues to progress. Now, many times scientists make the mistake of believing that science is the ultimate goal of what they're doing. And that's perfectly fine for some people. But if there are no people that understand that science is there to inform decision making, to inform product development, to inform tool development, and to improve the engineering practice, then we start creating poor translation tools, poor legislation, poor regulations, and as a result, we break the virtuous cycle. And this is something that we really need to keep in mind because this is really a fundamental issue that needs to be always kept in mind in that relationship between science, technology, and the creativity of architecture. So let's talk about fire safety then. So how does fire safety fit in all this picture? So we all know that when you want to have a safe building, you need to put together a fire safety strategy. That fire safety strategy is going to rely on very simple concepts that we all manage in a very appropriate way. So we're going to use compartmentation, which basically means we're going to create structures that are going to box the fire in such a way that the fire cannot expand in an uncontrolled way. We are going to control the growth of the fire by choosing the appropriate materials, by introducing suppression, like sprinklers, into the building in such a way that we create a fire that grows in a manageable way. We're also going to tell people that they have to evacuate by introducing detection and alarm. And that is going to give you a warning so that you can start moving out in an effective way before the fire starts affecting you in a negative way. And we know that we have some time available. That's the available safe egress time. What is that time available? Is the time that we have before things get too bad. And therefore, that time can be translated into a distance, because we can move at a certain velocity, and with a velocity and a time, we have a minimum or maximum egress distances that we need to play with to make sure that people can move from an unsafe place to a safe place fast enough. And then we need to protect, those safe places like the stairs in a tall building by making sure that smoke and fire cannot get into those spaces, because people are going to spend a lot of time walking down the stairs getting out of a very tall building. Okay? Now, all these things that we put in place create a strategy that tells you how the building works. And we know how to put all these things together to get safe buildings. This is why we have this feeling that the buildings in which we exist are safe for us. None of you feel that you are at risk right now. You all feel that you're sitting in this room and you're safely sitting in this room because we have put this fire safety strategy. Now, that fire safety strategy is underpinned by building regulations that are telling me that I need to put these things in place to make sure that this building is safe. Okay? Now, all safety systems require a redundancy. And if something goes wrong, there has to be something else that can pick up. I can put redundancies in the building, but the ultimate redundancy in the case of fire safety is always the fire service or the fire brigades. So if something goes wrong, firefighters can come in and they will intervene and control the fire and support us. So in essence, the fire brigades are the redundancy to the building safety. The building should be safe, but if something goes wrong, the fire service should come and pick it up. Now, as engineers, we owe to the fire service to give them a safe place to work. So in our fire strategy, we have to make sure that our compartmentation, our distances, our protection of the means of egress are done in such a way that it enables the firefighters to do their job safely. Okay, so I mean, there's nothing extraordinary about this, and these are all very simple concepts. Now, the question is, when you look at these two photographs, and these are two photographs of Shanghai, and this is the two sides of the river, and when you look at the change associated to these two photographs, you realize that there's been a very dramatic change in the last half a century. And in that half a century, we have transformed our cities enormously. And the question is, how has our science influenced our technologies, influenced our architecture, and influenced our regulation to actually cope with the dramatic nature of that change? So let me take you to an example that is a very painful example that we lived in the United Kingdom in the year 2017. So this is a Grenfell Tower fire, and this is a very simple, small 20-story residential building that trapped 72 people in a fire, and every single one of them died. So we had 72 casualties in this building in what is supposed to be one of the simplest possible designs that we have. Now, the Grenfell Tower fire was followed by what we call the Grenfell Tower Inquiry. The inquiry was an investigation that lasted 7 years that looked into why this happened and how and what changes do we have to make to try to prevent it. Now, you look at a building and there's two things that you have to understand. One is that this is as simple of a problem as you could possibly give to an engineer or to an architect. There's nothing simpler than a very, very basic residential building of medium height. Okay? The second one is that is the crash of this change. Why? Because this is a building that belonged to the 1960s, that it was designed and built in the 1960s, but it was refurbished in the 2000 2015s with technologies that belong to 50 years later. So in essence, we had an old concrete building that belonged to the 1950s or 1960s that was refurbished with modern technologies of the 21st century. Okay? So it created the convergence or the crash of two philosophies that were completely different. Now, if you look at the building, as I say, incredibly simple, 6 apartments, very small apartments, 4 2-bedrooms, 2 1-bedrooms, all around the central core with a single stair that is protected and 2 lifts. Very small footprint. The building was not too tall, was only 24 stories. And one of the simplest buildings to design, very few options and very well-defined solutions. This particular type of buildings is as simple as it gets because there's not much you can change. You don't have the space to change anything. There's very little you can do to transform that building. Now, this building was designed under the principle of stay put, which basically means that the safest place for people is to stay in the building. Now, how that works, the building is supposed to protect you. In other words, the compartmentation in the building will contain the fire to one unit, and then you privilege the firefighters who will come in through the stairs, use the stairs to bring their equipment and fight the fire in that unit and extinguish it. Everybody else stays in the building. That's the principle of stay put. It was a very robust and commonly used approach in the United Kingdom. Thousands of fires had had successful outcomes with a stay put strategy, and as a result, it was recognized as having a very good track record and something that everybody was confident in using. An external fire, by definition, will challenge the stay put strategy. Why? Because it will basically mean that the fire can move on the outside and therefore will not stay in the unit, and as a result, people cannot stay in the building. There were many precedents, and we've seen these fires happening everywhere around the world in the last 20 years. So it's not a new phenomena. It's not something unusual. It had already happened in the United Kingdom. It's a famous fire called the Lacanau fire. It had already happened. And just recently, a few weeks ago in Hong Kong, we had a very tragic event that is very, very similar to this. We've seen them in Dubai, in Australia, here in China. We've seen them in South America, in North America. Everywhere we've seen these fires. So basically, we should expect that those who designed this building should have been prepared and should have understood that that possibility was there and the design had to address it. Now, this particular building had aluminum composite panels, which is 2 plates of aluminum with a core of polyethylene. Now, is there anything new about this product? No, because the combustion properties of polyethylene, the signs, are very well known. The melting properties are very well known. The phase change properties are very well known. Pyrolysis is very well known. Combustion characteristics are very well known. And we've known most of these things since the 1930s. So this is not a material that was unusual or difficult. The science behind it existed, and we knew that science was there. Now, external wall systems have to support the life safety strategy. So if I use a stay put strategy and I have to contain the fire to one unit, then I know that the fire cannot get out. I know it has to be contained and it cannot enter the floor above or the side. So there's nothing new with this. If I'm going to use a stay put strategy, the fire has to stay within the unit. So there's nothing new. The external wall system has to deliver a fire that is within firefighting protocols. And in this particular case, because the fire was meant to be in one unit, firefighters came with equipment and personnel to fight a one-unit fire. We knew that. And despite the combustion of properties of polyethylene and in the external wall system, the external wall system must support the life safety strategy. There's no question about it. We know that. So what is that we didn't know? All the science, the knowledge necessary to understand this existed, but it was not used. So why? Since we knew everything since the 1930s and 1940s and 1950s, why we design a building in 2015 that trapped 72 people? If there was nothing new. This is a real question that we need to ask, because everything that happened was foreseeable. We knew it could happen. The science and the knowledge to prevent the outcome, the deaths, existed. So we had all that knowledge. Many of you are doing science in this particular space. We're all working to try to improve our knowledge, and we have created all the knowledge that is necessary to prevent this. So why did it happen? All those involved in the design, the architects, the engineers, in the construction companies, in the management, the building owners, should have had the knowledge and ought to have exercised that knowledge in the design, construction, management, and maintenance of the building. Why they didn't? We have regulations that tell them they have to. But why they didn't? Why did we sacrifice 72 people? Why did we sacrifice more than 200 people in Hong Kong? Why did we sacrifice 30 people in Madrid, in Valencia, in Spain? Why do we keep sacrificing people if we know everything we need to know to deliver the right answer? Where is the problem? It's not a scientific problem. It is a problem of us not using the information that we need to use. Now, it took 7 years to figure this out in the United Kingdom, and I think this is something that is really important, and it all stems from the changes of regulation, the translating tool. We changed the rules in 1984, but we didn't pay attention. And 30 years later, we have still not realized that our changes in the rules brought us to a point that despite having all the knowledge, nobody uses it. So, what is what happened? We changed from a very prescriptive system of rules that were very rigid to performance-based design. In other words, functional requirements. The building has to deliver some objectives. Now, this diminishes the hierarchy of the rules, so the rules are no longer rigid and important. They become just guidance to the competent professional who is supposed to deliver on the objectives of the building. Functional requirements plus guidance then now give you a solution. This is something that everybody in the field of fire safety talks about and has been talking about for 50 years. Performance-based design. We are ready. We have the tools, we have the science, we have the knowledge to actually use guidance to be able to deliver solutions by meeting some functional requirements. Now, the social responsibility, all science and knowledge for fire safety design had to exist. And we recognized in the 1980s that we had those tools. There had been a lot of fire research, a lot of science that got developed in the 1960s and 1970s that had been converted into technologies, into tools and models that enabled us to calculate everything we needed to calculate. So the social responsibility was there. We knew what that information was, and we knew how to do the things correctly. Was that enough? And this is where the problem is. There's one missing element, which is competence. We need the people that know how to use those tools, that understand their limitations, that understand their performance. We did not include that in the formula. We just said, we turn our rules into guidance, and now we give you some functional objectives that you need to meet. And we ignored the fact that we needed competent people. So we never regulated people to be competent. So what is the difference between performance solutions and prescriptive? Very straightforward. Prescriptive solution, you narrow the problem by means of a classification. You study it until you get a very good solution, and then you convert that into a set of rules that need to be respected to perfection. You cannot change anything. Everything is rigid. Architects hate that because it restricts creativity. Okay? Performance-based design, we have no classification. All we said is, here are your general objectives. Then you do everything else. You do the design, you calculate everything, and you prove you have met those objectives. If you can do that, then your building then is safe. So in a way, instead of doing your homework ahead of time and convert it into a set of rules for a very narrow set of buildings, what you do is you give people the freedom to just simply meet the objectives in whatever way they want. So the way we did it in Britain was in approved document B, and you can see B1, B2, B3, B4, B5. Those are the objectives. They're very simple. First one, people have to be told there's a fire and they have to get out safely. Second one, the fire has to grow slow enough so that people can evacuate safely. The third one, the structure has to withstand the fire and retain its function. The fourth one, the fire cannot grow outside the building, challenging the egress of people. And the fifth one, we need to give a good working environment to the firefighters. Those are your objectives. Now you do with that whatever you want. And we give some guidance, and you can see for external fire spread, we said the external walls of a building shall adequately resist the spread of the fire. What does adequate mean? The word adequate can mean anything, and it is the competent professional that has to decide, given the design that they're putting in place, what adequate means. Now, many people will say that a system like that cannot work because it's very easy to trick. You know, the word adequate can mean anything. But if you're a competent and responsible and ethical and moral professional, then you will actually use your knowledge and your skills to demonstrate that adequate fulfills the functional requirements. Nobody has to tell you how to do it. You can do it because you are competent enough. Now, the result was the transformation of London. And you can see the same as Shanghai. London went from a low-rise, traditional construction building into this extraordinarily modern 21st century city. We achieved the objectives of creativity, of architecture. Every famous architect will have a building in that set of buildings in London. So, you have Norman Foster, Richard Rogers, you have Raphael Vignoli, you name it. All the famous architects have buildings in there, and they all realized their dreams of constructing the buildings they wanted. We enabled that by creating this very simple system of functional requirements. So while many people will argue that this will not work, there is the proof that somehow it seemed to have worked. Nevertheless, it led also to Grenfell. So how do we do this? So we set our objectives, functional requirements. Okay? Those objectives have to be married in a fire safety strategy that tells us how we're going to achieve this, and we need to demonstrate for purposes of compliance that it meets the 5 functional requirements. That's it. That's all I need to do. Now, how can I do that? Well, I can use guidance or I can use engineering tools. Whatever tool is available to the competent professional, I can use. Okay? It's as simple as that. Now, if you think about it, who sets the objectives? The competent professional. Who creates the fire safety strategy? The competent professional. Who determines what the professional boundaries are? When the civil engineer stops, when the fire engineer starts, when the architect stops, when the facade designer starts, all these professional boundaries are determined by the competent professionals. And therefore, all the responsibilities are determined by the competent professionals. So as a result, you put an enormous dependency or weight on professional competency. Now, what are we doing as scientists to improve professional competency? How are we educating people to be able to use our tools or the science that we create to be able to do this correctly, given that the regulations that we created in 1984 actually give all the weight to that professional competency? How are we fulfilling our responsibility as scientists to society by educating people to be able to use these tools correctly? So this is a very big question because it's an enormous presumption of competency. You're assuming that the competency is there, and we keep doing our science and creating more and more and more complex tools, assuming that everybody knows how to use them. Many times we're even simplifying the use of the tool. When the fire dynamic simulator was created, a massive premise behind that tool was to make sure that all practitioners could use it. Make it as simple as possible so that all practitioners can use it. How are we guaranteeing that it's being used correctly? So that presumption of competency is very high. And when we look into Grenfell and we look at the tools that we use, we realize where the problem is. Because if I construct now the fire safety strategy for this building, I will say, well, fine. The objective is to give all occupants the best possible chance to be safe. Nobody will argue with that. Now, how do I do that? The first thing I do, if there's a fire, I tell them there's a fire. Detection and alarm. Once I tell them there's a fire, I box the fire. First by protecting the corridor, then by creating fire-resistant construction around the unit, then by protecting the stairs with fire-resistant construction, and then by putting smoke management in the corridor. 4 levels of redundancy in the path between the occupant and the safe place. Okay? Now, by doing so, I have boxed the fire and I have allowed the occupants to move out. Now, what does that give me? Nothing unless I achieve the same level of protection on the outside, because I need to box the fire also so it cannot grow on the outside. No? So, in essence, if I do that, then I can achieve my 1 unit fire. This is one of the biggest problems that fire safety has today, that in essence, the design fire is the outcome of the design process, is not the input. So my objective is to achieve a 1 unit fire, and as a result, I construct a system that delivers a 1 unit fire. And if I deliver a 1 unit fire, then people can stay put. And all those individuals that are in the building can actually stay there and not leave, because the fire is boxed. Okay? So that's what I did. Now, how does it translate to reality? I want a 1 unit fire. And to do so, I put detection, I put 4 levels of redundancy in my compartmentation, I guarantee no external spread, I protect the structure accordingly to fulfill its function, and therefore I have a safe area and people can stay put. That's the way I did it. Now, do I have redundancies there? Well, this is the building safety, and I have the fire brigade. That's my first redundancy. But I will put building management, maintenance, inspection to keep things going through the life of the building. But in essence, I put multiple detectors for redundancy. I have 4 levels of redundancy here. The firefighters are a redundancy. My structural design is done in a very conservative way, using very conservative methods. And nevertheless, everything depends on the fire not exiting the unit. Furthermore, I'm going to create a conflict, because I'm going to give the stairs to the firefighters to fight the fire, which inevitably is going to fill the stair with smoke, and nobody can get out. So, does that make sense to you? All the dependencies in a single point failure mode. At the end, whatever I do in the external wall fire has to guarantee that I can deliver the 1 unit fire. This is where we made the mistake. How can we be so stupid? This is obvious. Do you have to be a high-level scientist working in a leading laboratory to be able to tell me that if you cover the building with polyethylene, this is never going to work? How can we be so stupid? What is the responsibility that we have as scientists to make sure that the practice is not this stupid? That diagram shows you very clear where your problem is. And it doesn't require a great mind to be able to actually understand that. So, what's the problem here? Here we have our system, our translating tool. We know that in this case, adequate means no. Nevertheless, we've put a stay-put strategy with great confidence because it's worked 1,000,000 times. We actually have optimized by eliminating any alternative form of detection and alarm that allows me to get everybody out, because detection is only put in the unit. I have reduced the firefighting provisions to make sure that they can fight only 1 unit by sending less personnel with less equipment, and therefore I'm so confident that I've even optimized this. And all the science and knowledge necessary existed to conclude that this was a massive problem. How did we do this? Right now, in the United Kingdom only, there's more than 13,000 buildings being refurbished because of exactly the same problem. In places like China or Hong Kong, there's probably as many, but we're not even refurbishing them. We're just leaving them like that. How can we be so stupid? So, if you think about it, there's a massive inconsistency, because if we have this Building Act and we have this guidance, and we do not have a competency framework, this system is never going to work, because it's going to be populated by incompetent people that don't understand, don't even know about your science, that don't even know what we are producing and what we understand and what we know. And nevertheless, they are the ones who are responsible for delivering those buildings. What are we doing to change that? So 34 years later, when Grenfell happened, after 34 years of this new system of building regulations, we had created a massive technical and conceptual knowledge gap, where the practice is in a completely different place than the science, and the two of them are not talking to each other at all. Now, if you want me to prove it to you, very simple. Today, we're still using in our building design, in all the Chinese codes, maximum travel distances. Those maximum travel distances come from data that was gathered in a fire in 1911 that showed that in that particular fire in a theater, people had 2.5 minutes, that's 150 seconds, multiplied by the velocity of an individual evacuating gives you the maximum travel distance. So 1 meter per second multiplied by 150 seconds gives you the maximum travel distance. You put a safety factor of 3, and that's what you get. So this is what we're using today, 1911 technology, that actually tells me, because of a magician, the great Lafayette, that started a fire in a theater in the other side of the world, we basically have decided that the available safe egress time is 2.5 minutes. Do you know where that 2.5 minutes comes from? Is the duration of the British national anthem, the God Save the King. Why? Because during that fire, the orchestra played the God Save the King, so they had a number they could measure. That was the only experimental data point that they had, was the duration of the British national anthem. That became embedded in regulation, and we have retained that regulation since 1911. Every building in the world is designed using that number. Every single one of them. Can you tell me any other technology that still relies on 1911 knowledge? Do your phones rely on 1911 knowledge? Do your cars rely on 1911 knowledge? Now, that's not only the maximum egress distances. Smoke detection technology has not evolved since the 1930s. The technology of the smoke guard, which was the first smoke detector, was developed in 1939 by Ernest Mailey. It's exactly what you have in the ceiling of this room, and it has not changed at all. Can you tell me if your cars or your microwaves or your blenders work with 1939 technology? Sprinklers have not changed since 1897. Every sprinkler in this room, in the corridors, is designed using technology of the 1890s. Can you tell me if your desks were designed with technology of the 1890s? If your chairs were designed with technology of the 1890s? Fire resistance was developed in 1928 by Ingberg, and it still dominates the structural integrity of every single building that we design today. We know it's completely wrong. We know it doesn't represent a fire. We know it doesn't produce structural behavior because it doesn't produce temperature gradients. We have all the signs, but nevertheless, our practice is still using 1928 technology. The fire service has not changed its protocols and practices since the 1850s. And in their bookshelves, they still have James Braidwood's book that was published in 1856. So, why are we doing science? If you look at what has happened, science has evolved massively, but the practice has not. Now, if you look at the need, so if you have in the y-axis the existing knowledge in blue, the knowledge that we're using in green, and the knowledge that is needed in red, you will see that the relationship is very complex. The knowledge that we need keeps increasing because the technologies become more complex. Things like lithium-ion batteries come into play. All these things keep happening, so we need more. And we've seen massive increases in certain periods because of need. So during World War II, for example, there was a massive investment in fire technology because we were trying to destroy cities. So we needed to understand how to burn them down. In the introduction of plastics created very, very large fires. It was fueled what in the United States was called America Burning Act, which was a grant from Parliament or from Congress to try to fund research. Energy, with all the thermal insulation and so forth, has created a very significant additional need. Timber, with all the environmental concerns, has added a new need. And of course, lithium-ion batteries bring a whole new set of problems that we need to address. So that's a need. Now, where is the knowledge? Well, the knowledge most of the times lags. There are certain periods, like after World War II, where we actually learned so much that we were ahead. But then we fell behind when plastics entered. And then eventually we caught up in the 1970s with all the effort that was put towards characterization of flammability and numerical models and so forth. But now we've fallen behind again. So we have less knowledge available than what we actually need for the problems that have been created. Now, where is the practice? So the practice, despite the fact that we have all this science, okay, part of it you have developed here. All the science that started in the 1970s and 1980s and 1990s, despite that we have all this science, and you have all these really powerful institutes that were created all around the world, the practice peaked with one individual called Margaret Law, that is probably the one true fire engineer that actually really understood the problem. And then after that, the amount of knowledge that we use is less and less and less and less. So our knowledge gap is there. So there is a reason to do science. But our competency gap is huge. And we have to figure out how to translate that science in a way such that the competency gap is reduced and people start using what we are producing. Now, if I can just give you two very basic examples. In the 1980s, Ron Rim and Howard Baum developed the fire dynamic simulator, the first computational fluid dynamics model using very sophisticated turbulence model, the Smagorinsky model at the time, and delivered this wonderful tool. Okay? Nevertheless, despite all the evolution of FDS, the input that we still put in there is a design fire described by a very simple polynomial called alpha t squared. Not only is wrong, it doesn't represent the physics, is completely inappropriate given the complexity of the tool. So we are using a tool that we continue to invest in developing in a way such that is limited by the knowledge of 1980. Structural engineers have developed the sophisticated final element models, and structural fire engineering has developed massively. Nevertheless, we're still inputting, the parametric fire curves that Patterson developed in 1978. Knowing that the parametric curves are wrong, they represent a narrow regime of fires that don't reproduce temperature gradients, that create all sorts of inadequacies in the model. So we have a very sophisticated tool, as you can see in there, using final element models with complex heat transfer calculations and complex structural mechanic calculations. Nevertheless, the inputs are 1978's incorrect temperature time curves. How can we be so stupid? You see research papers, many of them, using the same inputs. Why? So we're still delivering 1960s fire safety for a 2030s world. Why? Because there's an enormous confusion of what being competent is, and it's all delivered by the absence or the poor regulations. So this is a consequence. So this is Richard Millett, the head lawyer of the Grenfell Tower inquiry. Behind him is the second person in command, Kate Grange. And this is the conclusion of the Grenfell Tower inquiry. First point was they exempt the owner of the building of any responsibility because the owner of the apartment, because the owner of the apartment, as soon as he spotted the fire, he left the building and called the fire brigade, and he was the first. The only person who did everything they had to do was the person who lived in that unit. In contrast, the evidence tells us that there was nothing unknown or not reasonably knowable which caused or contributed to the fire and its consequences. We just discussed that, no? We knew everything since the 1930s. Therefore, each and every one of the risks that existed at Grenfell on that night were very well known by many and ought to have been known by all who had a part to play. Pretty straightforward. As a result, you will be able to conclude with confidence that each and every one of the deaths that occurred in Grenfell on the 14th of June 2017 was perfectly avoidable. Those people died because of incompetence, poor practices, weak and incompetent practice, cynical and possibly dishonest practice, incompetence, weak and malpractice, acting despite known risks, failures of competency, training and oversight, failure by the London Fire Brigade to learn lessons, incompetence, incompetence, incompetence. How can we be so stupid? We're so stupid that all we know what to do is to point fingers at each other. And all the companies involved basically told is somebody else's fault, it's not mine. None of them did their job, but everybody insulted everybody. And this is what is called the web of blame. And each arrow represents one organization blaming somebody else. Until the end, after their incompetence was proven beyond doubt, they still argued that it was somebody else's fault. Why? Because they couldn't even understand what their own responsibilities were. So, this is what the judge described as deregulation by incompetence. In other words, you make everybody so stupid that nobody can communicate. And as a result, you can get away doing anything you want. And this is a real problem right now, and one that we have to be very conscious of. Why? Because when we look at an expensive building on the right and we look at a cheap building on the left, you realize that this inconsistency of regulations without competency leads to social inequality. Why? Because if you don't have the money, everything is done cheaply, with people with no experience, with no knowledge, with no competency, and there's no regulation that forces them to be competent. If you have the money, everything has a name, and people are proud of their designs. The architect will put their name on the building. The structural engineer, Irving Cantor, will put his name on the building. Why? Because the investment was made, the effort was made, the detail was put in there to deliver something that is safe. So the poor are unsafe, the rich are safe. And we are responsible for that because we are the ones that have not delivered the competency. So this is how the virtuous cycle becomes a vicious cycle. Because the moment that you break it by not producing competent professionals, then the legislation evolves in an inadequate way because government is poorly advised. And as a result, they produce poor results. The positive outcomes disappear and they become negative, which basically destroys the social benefit by delivering social inequality. And as a result, people lose confidence on the investment in research. Or even worse, they put all their money in the wrong place, unused science. Not only that, so instead of new developments that are appropriate, what we get is unused technologies that sits in shelves because the regulation doesn't allow you to use it appropriately. And as a result, the virtuous cycle becomes a vicious cycle of incompetent practice. So, in the absence of competency, the virtuous cycle becomes a vicious cycle. And this is unfortunately where we are today. And we know what we do not need to know, but we do not know what we actually need. And this is a real problem. And we spend our lives doing research that at the end sits in shelves. Why? Because people are still using 1911 technologies. So, to finish, professions have attempted to define competence for centuries, but we have to understand that competency is not something that we decide. We are not competent, you're deemed competent. Somebody has to say that you're competent, and this is where our role is. Professional competency has to be regulated when the subject is one deemed to be complex and important for society, and fire safety is complex and it is important for society. And it is our responsibility to be able to anoint people as competent in the most effective manner as possible. In 2018, an event that was well understood, that left major questions on the competency of all those who played a part in the design, building, and management of Grenfell Tower, but also on all those who developed the legislation, performance tests, and practice protocols that allow Grenfell to happen, particularly on those who anointed the competency. And this is where our role as a university is. It is the job of a university to anoint competency. And if we are not exercising that responsibility properly, effectively our science is going to end up all in bookshelves. At this point, we have reached a level of total loss of trust in the United Kingdom. I presume that the same thing is going to happen in Hong Kong. And this is going to continue to propagate around the world. And we have to be very, very careful that we take our responsibility seriously and we try to turn this around because we are responsible to do this. So the future is to try to recover trust by properly defining and enforcement competency. And the reality is that this is our responsibility as academic institutions, as research institutions that actually believe in research-led education. So thank you very much for your attention.